Students, can you hear me now? Okay. Sorry, there was a problem because of which I was not able to send my voice to you. Okay. Welcome to virtual session of week 10. So we were talking about relational algebra previously in our previous lectures. But in today's lecture, we are going to talk about formal relational query languages in more detail. So let's continue with the lecture. During the lecture, if you have any question, you can just raise hand. I'll stop there and to answer your queries. And also, if you have some question about any previous lecture as well, you can ask me at the end of this lecture. So we have to talk about formal relational query languages, relational algebra, about tuple relational calculus, about domain relational calculus. You may be familiar with these operators, which we have studied before as well, and there was a question from these contents in your exam as well, that there are 6 basic operators used in relational algebra for databases. One is select operator, other is project operator, union operator, set difference operator, Cartesian product operator, and rename operator. These operators take one or two relations as inputs and produce a new relation as output. Now relation is, I hope you are now familiar with the relation, and if I'm saying relation and if I'm saying table, it means I mean the same. So let's talk about each of these operators one by one. So first talk about the selection operator. Selection operation, select certain rows or certain records from your relation. For example, if you have a relation R having attributes A, B, C, and D, and you apply selection operator, like for example, if you see that this selection operator is selecting the records, the information where value of attribute A and B are equal, and now this symbol is used for and the value of attribute D is greater than 5. And from where to perform the selection? From the relation R. So all the rows where value of A is equal to B, like alpha is equal to alpha, B is equal to beta, and the value of D is greater than 5 are selected. Now if you see from here that A is equal to B over here and the value of D is greater than 5, so it is selected. Now here A is not equal to B, so we skip this. Here A is equal to B, but the value of D is not greater than 5, so it is not selected. Here A is equal to B and the value is greater than 5, so it is selected. So you can select certain rows based on the conditions given in your selection operator. Now the selection operation notation is this. The symbol is used for selection. This P or row, sometimes it is called selection predicate. This P stands for predicate. It is defined as the selection operator is equal to T, which is where T is also a relation, and selection predicate applies on P, where P is a formula in propositional calculus consisting of terms connected by and, or, and not operator. Each term is one of the attribute, operator, attribute, or constant, where op is any operator which is equal to, not equal to, greater than, equal to, less than, or less than equal to. Now the example of selection can be select from instructor table those records where department name equal to physics. So or those rows, those records will be selected where the department name equal to physics. And so it means all the details about instructor teaching in physics department will be brought by using this selection operator. Now another operator is project operator, which is used to select certain columns. So when I say columns, I mean the attributes. So from a relation, if you want to highlight or you want to extract certain attributes and the values of those attributes, you can use the project operation or projection operator. For example, if you have a relation R with 3 attributes A, B, and C, and you want to get only 2 of them, then you can use projection operator in this way and project only those columns which you want to use, A and C, suppose, from this relation R. So the output will be this one, and whenever one of the record is getting repeated, like alpha 1 is appearing twice, so this can be eliminated and you can have a concise relation in this way. The notation is used is the projection operator, the attributes in a sequence like A1 up to AK, and R is the relation. The result is defined as a relation of K columns obtained by erasing the columns that are not listed. So from a relation where, for example, there are 10 columns in a relation, and you want to extract only 3 or 4 columns, so you can select from only those 4 columns instead of loading the whole relation or table again and again. So you can only utilize the information which is required. Duplicate rows are removed from the results since relations are set. To eliminate the department name attribute of instructor, you can, for example, instructor table was containing the ID of instructor, name of instructor, salary of instructor, and the department name of instructor as well. But you don't want the details about department name, you only want the details about instructors with ID, name, and salary. So you can project only ID, name, and salary from instructor relation. Another operator is union operator, in which you combine 2 relations. For example, you have a relation R and you have a relation S. So when you want to merge them up, you make a union. For example, if you see that alpha 1 is over here, so you include it in this. Alpha 2 is here and here as well, so you include it. Beta 1 is here, so you include it. Alpha 2 is already included. Beta 3 is there, so you include it. So you are merging both of those relations. So union operator is used for merging. For R union S to be valid, and R and S must have the same arity. It means they should have the same number of attributes. So it means whenever you want to apply a union operation on a relation, the number of attributes and the sequence of those attributes should be same. So if they are different, then you cannot merge them. Example can be to find all courses taught in fall 9th semester or in spring 10th semester or in both. So you can make a selection in this way, like project course ID, because you want to find courses. So you are to find courses. If you have find course ID, it means you can get the rest of the details from the courses table. So course ID is actually uniquely identifying a course. It's the primary key of that table. So you project course ID, and how you project, you select where semester is equal to fall and year equal to 2009 from the section, and combine it with the projection of course ID from the section table where semester is spring and year is 2010. So in this way, when you are projecting the course IDs from fall 9 and spring 10, and then you are doing union of that. So you will get a list of all the courses taught in fall 2009 semester, or in spring 10 semester, or in both. So you are merging them up. There is a set difference operator as well. Like you have a relation R and you have a relation S. So you want to find the difference. It means you want to identify those attributes of R which are in R but not in S. So those attributes of R which are unique and not found in S will be identified. So in this alpha 1 and beta 1 which are in R but not in S are identified. Similarly, if you want to perform S minus R, so can you tell me that what would be the output if I do it in a reverse way? So what would be the output if I do S minus R? What would be the output if we do S minus R? Okay, think about it. I'll ask you later. Okay, I'm just going to, because we have already studied these contents, so now I'm going to be a little quick. So this is the details about this. Like, you want to find all courses taught in 2009 but not in spring 10, so you can use the difference operator. So then this is the decision which you have to make, that when you have to use the which operator which you have to use for these things. Then you have a Cartesian product operation in which you can have a Cartesian product. For example, if you have R and S, so you'll combine each row of R with each row of S with S, and in this way you'll get a relation which is greater than, which is merging up or combining both the relations. Now you can build expressions using multiple operators as well. Like, you can perform R cross S, and then you can select only those rows where attribute A is equal to C. So you are combining two operations over here. There is a rename operation which allows us to name and therefore to refer to the results of relational algebra expressions. Allow us to refer to the relation by more than one name. For example, this expression returns the expressions E under the name X. So in the relational algebra expression E has arity n, then this statement returns the results of expression E under the name X and with the attributes renamed to A1 up A2 up to AN. The queries can appear like this. For example, you want to find the largest salary in the university. So first what you have to do is find instructor salaries that are less than some other instructor salary that is not maximum. So you can use a copy of instructor under the new name D, and you can perform selection in this way, and after doing this then you can find the largest salary. You are projecting the salary column from instructor table and you are calculating the difference from instructor.salary, where salary is less than the salary of the instructor. So you can write queries in this way for every expression, or you can write expression for every query. Similarly, the query can be find the name of all instructors in the physics department along with the course ID of all the courses they have taught. So this sounds complex initially, but if you see that, if you read it from here, from the inner one, you will see that first of all what you are doing is you are combining two relations, instructor and teachers, because here you are interested to know about the teaching details as well. So when you identify and make a combination, Cartesian product of instructor and teachers, it means all the details are recorded. Now you can see where instructor ID is equal to teacher's ID. It means because you have to find the names of all instructors, so instructor will be the output, and you have to identify the instructors from the physics department. Okay, so from the physics department means you may have to make a selection from physics department only, along with the course ID of all the courses they have taught. So it means you want a list of all instructors of physics department with the list of course IDs which they have taught. So what you will be doing is you will see that where instructor ID is equal to teacher's ID. So from the teachers and instructor table you will identify the subjects which are taught by those people, and then you will select only those instructors which are from physics department. So first doing it for instructor, you will select the ones from physics department, and then you will project instructor ID and course ID, because you had to display the names of instructors and the names of courses they have taught. So instead of doing it in names, because names are not can be repeated as well. So you are doing it with IDs, like you are projecting IDs and course IDs. This can be done in a different way as well, like instead of first making selection from all instructors, what you do is first you pick up only the instructors from physics department, and then you match their IDs. Instead of doing it for all and finding the details about all instructors, what you are doing is first identifying which of the instructors are from physics department, and from the physics department instructors, you match on IDs of only those instructors with the teacher's ID. So this is another way. A basic expression in the relational algebra consists of either one of the following: a relation in the database and a constant relation. Let E1 and E2 be relational algebra expressions. The following are all relational algebra expressions. Like you can make a union, you can form a difference, you can, even if E1 and E2 are individually in expressions, so you can write them in this way. So there is no limitation that how much nesting you can perform. So you just need to understand it well, and whenever you are trying to resolve it, you try to resolve it from the innermost level. We define additional operations that do not add any power to the relational algebra, but that simplify common queries like set, section, national join, assignment, and outer join. We have already talked about this, so I'm going to skip this because we have already done this part. We've already studied about join operators and outer join operators. Now, how to deal with null values? It is possible for tuples to have a null value denoted by null for some of their attributes. Null signifies an unknown value, or that the value does not exist. So even if a value does not exist or it is unknown, so you mark it in a relation as null. The result of any arithmetic expression involving null is null. Aggregate functions simply ignore null values. For duplicate elimination, and grouping null is treated like any other value, and two nulls are assumed to be the same as in sequential structured query language. Given relation R and S, R division of S is the largest relation such that T cross S is a subset of R. For example, let R ID course ID is a relation in which so when you use the division operator in this example, it gives us the students who have taken all courses in the biology department. And there are certain external relational algebra operations like generalized projection and aggregate functions as well. Generalized projection extends the projection operation by allowing arithmetic functions to be used in the projection list. So you can use those operators, the relation operators over here as well. And in aggregate projection, aggregate functions and operations takes a collection of values and return a single value as a result, like you can use average, minimum, maximum, sum, and count. So this is the aggregate operation for relation R. You can take a sum of column C. Similarly, you can find the average salary in each department using these operations. The contents of the database may be modified using the following operations: deletion, insertion, and updation. All these operations can be expressed using the assignment operator. Now, multi-set relational operators. Since wait for a second. Okay, I'm back. Pure relational algebra removes all duplicates. For example, prediction. Multi-set relational algebra retains duplicates to match SQL semantics. So these are the operators which we have already studied. So I'm going to skip these things. Now, when we talk about SQL and relational algebra, SQL statements can include the expressions from relational algebra in this way. Like, for example, you can say that select A1, A2 up to AN from R1 up to Rm, where P is equivalent to the following expression in multi-set relational algebra. So this can be written in this way, where you are using the aggregate operations as well. More generally, the non-aggregated attributes in the select clause may be a subset of the group by attributes, in which case the equivalence is as follows. Like, select A1 and sum of A3 from this, where P grouped by A1, comma A2. Okay, now before proceeding further, I want you to first let me know if you understand the things we have studied so far. We have talked about relational algebraic expression, the relational operators. So if you have any question from these contents, you can ask me now, and then we'll proceed to the rest of the contents. Okay. Tuple relational calculus. Let's talk about this. A non-procedural query language where each query is of the form T and predicate. It is a set of all tuples T such that the predicate P is true for T. T is a tuple variable, and T of A denotes the value of tuple T on attribute A, and T belongs to R denotes that tuple T is in relation R, and P is a formula similar to that of the predicate calculus expression we have studied previously. Now, in predicate calculus formula, there are certain attributes and constants. There are certain comparison operators, set of connectives like and, or, and not, and the implications. For example, the implication operator, like if X is true, then Y is true. And the set of quantifiers, like there exists a tuple in T in relation R such that predicate Q is true, or Q is true for all. Now this operator, this E, which is in the backward direction, is used for there exist, and this A, which is upside down, is used for all. Some example queries are mentioned over here like this. For example, find the ID, name, department name, salary for instructor whose salary is greater than $80,000. You'll select a tuple T where T belongs to instructor and T salary is greater than 80,000. As in the previous query, but output only the ID attribute value. So you want to select only the ID attribute, so you can do it like this, that there exists S belongs to instructor, where TID equal to SID, and the salary is greater than 80,000. And another one, find the names of all instructors whose department is in the Watson building. So it will appear like this because you want to find the names of all the instructors. So from the instructor table, you select the tuple names and T name equal to S name, and there exists U belongs to department, where department equal to department name and building equal to Watson. Or find the set of all courses taught in this, so you can write it in this way. So there are multiple ways to perform a single operations. It is possible to write tuple calculus expression that generates infinite relations. For example, you can write T such that not T belongs to R results in an infinite relation if the domain of any attribute of relation R is infinite. To guard against the problem, we restrict the set of allowable expressions to safe expressions. And an expression is safe if every component of T appears in one of the relation tuples or constants that appear in P. You can do universal quantification as well, for example, to find all students who have taken all courses offered in the biology department. So you can select them in this way, like T, whether there exists R relation R, which belongs to student, and the tuple ID is equal to the relation ID, and for all U belongs to courses, U department name is biology and takes that course. Now without the existential quantification in student, the above query would be unsafe if the biology department has not offered any course. So when you are writing the courses, you need to be very careful about this, that the query should give you some output and it should not be infinite. A non-procedural query language equivalent in part to the tuple relational calculus, each query is in the expression of the form this, and we can write queries in the domain relation calculus in this way, that as you can see over here, that instead of writing the queries, I'm using certain notations to express these things. I have skipped last few slides, the example slides, because to understand these, you need to have in-depth understanding of the tuple relations. And tuple relational calculus. So I want you now that you go through the tuple relational calculus slides in detail from your textbook, and then read these slides about domain relational calculus. And then I want you to come up with questions in our face-to-face class. So please read this material. There is no assignment in this week. Read through all this material, and then I expect that you'll be asking me questions in our coming face-to-face class. And about your midterm exam, I just want to say that your marks will be uploaded over the Blackboard during this week, and you'll be able to see your answer scripts on the coming face-to-face class. Okay, anything else you want to ask, or you have any query about this lecture, about previous lecture, or anything, you can ask me now. I'm turning my microphone off. If you have any question, just type your question and I'll reply to you over there. Thank you very much, students, for being patient.